Hello everyone and welcome to Network Playroom. This is the 12th video in the Christmas calendar series, and today we're going to look at the spanning tree cost and port priority. But before we get into that in more detail, let's briefly review the steps in the spanning tree topology calculation. So again, the three steps are: number 1, selecting the root switch; number 2, finding the best path to the root switch; and number 3, blocking redundant links. So the cost and port priority are involved in the last two steps. But first, the root switch is determined by the bridge ID, as you've seen extensively in previous videos. And then the best path to the root switch is determined by the lowest cost. And any ties are broken with the port priority. And this is easiest to explain with an example. So let's look at the diagram. So let's take the same old spanning tree topology we've seen before. Switch A is the root switch because of the lowest MAC address. So switch A right here. Here you can see the bridge ID. And then of course the first part is the bridge priority and the second part is the MAC address. And then FA0/1 on switch B is the root port, or the best path to the root switch, right here. This is the root port. And why is that? Well, it's because it has the lowest cost. So by default, the spanning tree cost for FastEthernet or 100 meg interfaces is 19. So this one would be the cost of 19. In fact, all of these links have a cost of 19 by default. So the other path to switch A or the root switch is through switch C with a cost of 19 plus 19, so 38. And hence, this is the root port or the preferred path. It has the lowest cost. But we could make this interface the root port by changing the total path cost to lower than 19. And that means we would have to modify both of these links to make the total cost lower than 19. So let's say we changed both of them to 1, making the total cost 2. So let's scratch over this and change into 1. So now the total cost is 2. And this port would become the root port. And this one, so FA0/2 would become the new root port, and this one would be blocking. So it would be a role reversal. You would see this one alternate blocking, and then this one would actually become the root and forwarding, with a cost of 2 this time. But that's really how the spanning tree cost works. But now let's go back to the original scenario and revert these costs that we've just changed back to their default values, which was 19. So let me clear out this information and start from a new layer. Okay, so we're back to the original setting, and the costs are 19 on all these interfaces. So FA0/1 is the root port again, right here. Root port. So let's add another FastEthernet link between switch A and switch B. So let me draw that in here using this ruler. So there we go. Now we have another link between the switches. Let's call this interface FA0/10, for example, on both ends. Like that. So one of these interfaces must block. And which one is it going to be? Well, that is defined by the port ID. So the port ID consists of a configurable priority value and the port number, which iOS assigns. So let's look at the output here. And as we can see, the port ID for FA0/1 is 128.1. So 128 is actually the default port priority value. And also note that the interface number and the port number don't always match. But let's say that for the new FA0/10 interface, the port ID is 128.10. So let's add that in here. So it would be also alternate blocking with a cost of 19 and a port ID of 128.10. So in spanning tree, lower is better. So since FA0/1 interface port ID is 128.1 and is lower than the port ID of FA0/10, which is 128.10, the FA0/1 interface will remain as the root port. So because 128.1 is lower than 128.10, that's why FA0/1 is the root port. So how can we change the FA0/10 interface to become the root port? Well, we can either lower the port priority on the FA0/10 interface or increase it on the FA0/1 interface. But let's do the first option. Now, pay close attention in this part because I was talking about the interfaces as I was referring to the local switch or switch B. But where do you configure the port priority? So you might think you would obviously configure it on the local interface, but that is incorrect. So the port priority is actually configured on the upstream device, in this case the root switch itself. So the configuration does not go on here, it goes on here. So this is somewhat counterintuitive because the locally configured cost affects the best path choice, but the locally configured port priority on the same interface basically does nothing. But perhaps the best way to remember this is that spanning tree calculations are based on the received PPDUs, and the sender port ID is one of those values. Well, the cost is sent in the PPDU as well, but that is a little bit different because you have to factor in the total path cost. So if you only consider the cost the upstream switch advertised without adding your local cost, you could have a 1 gig link and a T1 link considered equal. So let's say switch A wasn't a root switch anymore, so it was advertising some cost towards switch B, let's say 100. So if we would only factor that on switch B, so switch B receives that 100 on both of these interfaces, but they have totally different speeds, it's gonna look like these links are equal if we're only evaluating the cost received from another switch. So that's why you add the local cost to get the total path cost. But that's really the difference between those two values, the cost and the port priority. So to summarize, if you want to affect how the local switch selects the root port, change the cost value. But remember that you must consider the entire path. So total cost must be the lowest to become the root port. But if you want to affect how the downstream switch elects the root port, change the port priority. And this is only locally significant between the two directly connected switches. And again, the lowest value wins. So it's really interesting when you configure the port priority because, as I mentioned, you would have to configure it here on switch A. So let's say that you made it lower, so you did something like 64 instead of 128. So you would not see it in this output. You would still see this value, but what would have changed is that instead of this being alternate blocking, it would have become the root and forwarding. And this would have gone alternate blocking, which is really confusing because you're looking at the values, you're looking at the cost, they are equal, and this actually has a lower priority locally, so you would think that this would win, but no, it's this interface. But I'm hoping to show you this in a lab soon because it's really easier to demonstrate that way. And it's quite funky to configure something, but not seeing it take effect and produce the output you wanted. But that's it for this video. Thank you again for watching, and I'll see you in the next video.